Hi guys, in this video we are going to continue with our discussion of functions, and in today's lesson we want to look at domains in a bit more detailed. You see that? So in our previous lesson on functions, we learned about various ways in which functions can be represented, and we discussed the arrow diagrams as well as the representation of functions using explicit equations. You see that? So one thing that definitely is clear when it comes to the arrow diagrams is that when you have a function represented in the form of an arrow diagram, it is easy to tell what is the domain and what is the range of that particular function, or what is the codomain. You see that it is easy to tell those things. But now when you have a function which is such that it's represented using an explicit form whereby you are given the description of a function in some sort of a mathematical expression, then you will see that it is not clear then from there what exactly is the domain or what exactly is the range of that particular function. You see that? So in today's lesson, we are going to look at problems of that nature, where we are going to learn how to actually find domain of functions represented explicitly. You see that? So the things that we are going to focus on mostly, which are going to form the objectives of this lesson, are first, I will give an introduction of what we call the interval notation. So we are going to look at something that will be quite useful in the discussion, which is the interval notation. And then the next thing is we are going to look at how to find domains. You see, and more specifically, we'll look at domains of the following set of functions: a linear function, a parabolic function, and then also we look at an exponential function, then also we look at what we call a rational fraction, then functions with square roots. You see that? So those are the things that you are going to look at. And also, yes, we are going to look at also logarithmic functions. So that's what we want to try and uncover in this lesson, to try and understand all these information, to see how we can learn to find domains of these specific functions. You see that? Okay, so first thing first, now we are going to start looking at the interval notation. You see that? So what exactly is the interval notation? So far from high school, if you all can recall, there were times where you actually learned how to solve inequalities. You see that? And we know that during our time when we're solving inequalities, the solutions that we obtained, they came out in having different structures, and some of those structures were expressions like these. At times you had maybe something like x greater than some value a and less than or equal to b, or sometimes you have x greater or equal to a or less than b, or at times have a less than x less than b, and many other different variations. There were also many other different variations of these, or even a less than x less than or equal to b. But those are things that were quite common, mostly when you're solving inequalities. You see that? And sometimes the solutions, they came out as just simple s greater than some value a, or x greater than a, or x less than some value a, or x less than or equal to some value a. So all these were different variations of solutions that we were obtaining when we were solving inequalities. You see that? And so what we're going to do today is we are going to learn the interval notation, which is another way of actually writing all these different things that we are seeing there. You see that? So we have sort of a nice compact way in which we can write all these intervals. So any inequality solution which is written in this manner, we refer to those solutions as intervals. You see that? So the interval notation is just another nice way of rewriting this same information. You see that? So it's quite good to get familiar with it, because some books, they actually tend to use it quite often when they are trying to give you or to specify the domain or a range of a particular function. So it may be a good thing for you to get used to the interval notation at an early stage, so that at least whenever it's used, you are familiar with whatever is going on. You see. So now let's understand then how it works. How can we represent all these different things that I've written there using interval notation? You see that? So to see how it works, this is how exactly it works. So something like x is less than or equal to b can be written using interval notation as simply saying that x is an element, or then you open a square bracket, then a to b. You see that? So one thing that you can simply say is that the interval notation is something which makes the following transformations. You see that? So how it works, to put it in a much more nicer way, is that every time when you see the less than or greater than sign, this is actually replaced by the bracket, with this square bracket or the open square bracket, like that most of the time. So it's just that now it won't make sense as to exactly what I was trying to say here. So let me just write down how we can interpret all those things using the interval notation. So if you have x greater than or equal to a and less than or equal to b, this interprets in interval notation as saying x is an element of open square bracket a to b, then you close your square bracket like that. Then what if now you have just x less than a less than b? You see that? So here this can be interpreted as saying x is an element of a to b. So exactly what we can say here is that every time when you are using interval notation, it is a notation which makes use of an open and a closing bracket with the end point and the closing point of an interval written next to each other in the comma dot notation that we are seeing there, like that. You see that? But what you should pay attention to is things like these. So every time when you have the less than or equal to sign, it is always replaced using a square bracket. You see that? Whilst if you just have a strictly less than or a strictly greater than symbol, it is always represented using round brackets. So you will see that if you have something like x is greater or equal to a and less than b, then this can be interpreted as x is square bracket because there is a greater equal to on the left, and on the round a round bracket because you have a strictly less than on the other side. You see that? So it is the same thing again, even if let's say now you say x greater than a less than or equal to b, this interpreter saying x is just an element of a to b, where we use a square bracket for the greater equal to symbol, and for the strictly less than or greater symbol, we just use the round bracket. You see that? So this is how you can rewrite all those things that we have written before. What about half intervals like this one? So how would you interpret in interval notation x less than or equal to b? You see that? So x less than or equal to b, it simply means that x can take all elements from negative infinity to b, where b now, since there is a greater or equal, we use a round bracket. You see that? So one thing that you should know about half intervals, they can be written as full intervals, but the end point of the end point of a half interval can either be plus infinity or negative infinity. You see that? So if you have something like this as x is less than or equal to b, then this can actually be completed to see that it means from minus infinity to b, like that. So this then makes it to be interpreted. But every time, whenever you are choosing a bracket for the infinite end or the negative infinite end, so for the infinite end or the negative infinite end, we always use a round bracket, always. You see that? Because infinity is an unreachable point. So you can't say, you can't use a square bracket, because square bracket, it has a possibility of equality. So there is no way a number can be equal to infinity, because it's an unreachable endpoint. So that's why now you can't have that. So, and even things like x is greater than a, also interpret as for it. It means x is just an element from a to infinity the other side, because we see that we just say is number greater than a. So it means when we are to complete it, it means it has to be less than infinity, like that. So this is how the interval notation works most of the time. You see, so this is how it works. But what if x can take everything? You see that? So sometimes x can be a number which takes everything in the real plane. How to interpret that? So this is interpreted as saying from negative infinity to infinity, like that. You see, so this is how the interval notation works. So it's a good thing to be aware of how to make use of the interval notation at this stage before you start looking at techniques of how to find the domains or the range of different types of functions. You see that? So now that we have seen, or we are now aware of the interval notation, it is a good time now to start looking at domains. You see that? So the first thing that we're going to look at is the domain of a linear function. So first, what exactly is a linear function? So a linear function is a function of the form f of x is equals to ax plus b, such that both a and b are elements which belong to real numbers. So every time when you have a function which has this structure, this is what we refer to as a linear function. So sometimes you can be given a linear function in math, and you can be asked to find what is the domain of that particular function. You see that? So how exactly is the strategy, or how exactly does one go about finding the domain of any function? So every time when you are tasked with an assignment or to find a domain of a particular function, the only way you can actually answer this question is first to understand the question itself, and then to understand what is the best way to go about that. You see? So when we ask for the domain of a particular function, what exactly are we asking for? Yes, yesterday we gave a definition of what the domain is, but this thing that is referred to as the domain, it can be rephrased in different ways depending on the nature of the problem at hand. You see that? So if you have a problem which is asking you to find a domain of a particular function, you have to have a new definition of the domain. And how can we redefine the domain? You see that? So remember, what is a function? A function is a device which is such that it accepts something which we call as inputs, and it gives you outputs. You see that? But one of the things that you should know is that not every input has an output. You see that? So there are some inputs that you put into a function and you don't get anything out. So when we are asking for a domain of a particular function, we are simply asking you to tell us what are the possible values or possible values for inputs that can be put into the function, and we can get outputs afterwards. You see that? So the set of all things that if you put into a function you get outputs is what we call the domain. You see that? So that's exactly the approach that you use every time when we want to find the domain of a particular function. So for a function like this one, every time when you are given a function explicitly, if they say find the domain, the question that you should always ask yourself is there a particular input that I can put inside here and I do not get anything out? So if you are to look at a linear function, you will see that there is nothing that you can even imagine that you can put where there is the x variable there and you don't get anything out. For each x variable that you put, you will always get something out. You see that? Which means in general, the domain of a linear function is simple x element of real numbers. You see that? So which means every time when you're given a linear function, the domain of a linear function is always x element of real numbers. You see that? Unless maybe you are given a function already with some restrictions, whereby we tell you that this function can only take values greater than 5. It means your domain now will be all values of x starting from 5 and onwards. But if there are no restriction imposed on a linear function, it's a domain in general will always be x element of real numbers. You see that? So that too is going to be like that at all times and it's never going to change. Then the next thing that you want to look at is the domain of a parabolic function. So the domain of a parabolic function also, it is quite obvious like the linear function, but first let's understand what exactly is a parabolic function. So a parabolic function is just a function f of x which takes the form ax squared plus bx plus c such that both a, b, and c all belong to the real numbers. So that's what the parabolic function really is. Sometimes it's called the quadratic function, but the suitable name is parabolic function. That's how it looks in general. You see that? So examples of such functions, they'll be like f of x is equals to 3x squared minus 1, or g of x is equals to 5x squared plus 2x minus 3. All these are different examples of what we call a parabolic function. You see, so the question now is, what is the domain of this object? So the domain of a parabolic function is also in general x all real numbers. You see that? So domain of parabolic function is x element of real numbers. So those are things that you should know again, that when it comes to parabolic function, everything that you put, you always get an output. There is nothing that you can put and not get anything. Whatever you put, you always get a result at the end of the day. So this is how you actually find the domain of a parabolic function. Then next thing that you want to look at is the domain of an exponential function. So how do we find the domain? First, let's define what is an exponential function. So an exponential function is a function of the form f of x is equals to a dot bx plus c, such that both a, b, and c are elements of real numbers. And yeah, so it's defined like that. And mostly we'll prefer b to be greater than 0 always. You see, so we'll always prefer b to be greater than 0 always, because if b becomes a negative number, it will give us a lot of problems in many cases. So we always prefer b to be greater than 0 most of the time. You see, so one of the things that you should know now when it comes to the domain is that the domain of an exponential function is also x element of real numbers. So all these functions that I've stated, the linear function, the exponential function, and the parabolic functions, they are characterized by the fact that whatever you give them, they will always give you outputs. You see that? So this is one thing that you should know about them. But this is not something which is true for all functions. It's not always the case that every function can take anything and give you output for whatever you put in it. There are some functions which reject some other things. And now we're going to look at such functions which cannot take everything. You see. So the next function that we want to look at, which can take things and reject some things, is as follows. So the first one that we want to look at is what we call the hyperbolic function. So a hyperbolic function is a good example of a function that cannot take everything. So what exactly is a hyperbolic function? So a hyperbolic function is a function of the form f of x is equals to a over bx plus c plus t. So it is a function which has this form with a, b, c, d, all elements of real numbers. You see that? So one of the things that then you should know is that a hyperbolic function, it has to have this general structure such that there is a rational fraction with a linear numerator in it, a denominator in it, like what you can see there. You see that? So one of the things of the facts that we use every time when you're dealing with the rational fractions, like this one, like the hyperbolic function, it is based on this region. So there is one thing that you should always know every time when you have a fraction. You see that? So fractions can never have a denominator of 0. You see that? So fractions are characterized by the fact that they can never have a denominator which is 0. You see that? So from the fact that we know that any fraction can never have a denominator that is 0, it means if you have a function which is like this, whereby x varies or changes the denominator of that particular function, it means we must be careful to not put things that might cause that whole denominator to vanish, because once it vanishes, there is no output that you get from that. You see that? So it is from this fact now where we can actually then be able to come up with domains of things like hyperbolic function. You see that? So in general, what exactly is the domain of a hyperbolic function? You see that? So a domain of a hyperbolic function is x element of real numbers, but here now there is a restriction. There is something that x cannot take. So x cannot be equal to negative c over b, because if you are to put negative c over b, that denominator will become 0, so which messes everything up. You see? So to practice now how to find the domain of a hyperbolic function, let's look at a few examples. You see? So there are some examples that you can get in exam, like this one. They can ask you the following question. So it's an example 1. Given f of x, which is equals to 3 minus 2x over 7 minus 5x, find the domain of f of x. You see that? So how can you get to answer a problem like this one? So to answer a problem like this one, this is how we proceed. So first we check what do we see. So we see that we have a function which has a denominator. So every time when we spot a denominator, we now know that this is where our solution will come from. So what do we know about any fraction in maths? We know that for any fraction, the denominator cannot be 0. So which means from this it follows that we know that 7 minus 5x cannot be equal to 0. So this implies 7 cannot be equal to 5x, which implies that x cannot be equal to 7 over 5. So therefore, the domain of f, which we write as dom f, is just simple x element of real numbers, but x cannot be equal to 7 over 5. But usually we don't prefer to write solutions this way. We usually prefer to write the solutions using the notation that we have introduced, which was the interval notation. But how can you write something like this using interval notation? You see that? So you know that this function f that we have here, it takes every real number except 7 over 5. So how can we write this now using interval notation? So to write this using interval notation, this is how we proceed. So we see that we have to have everything except 7,5, which means I can take everything from negative infinity, but since I don't have to take negative 7,5, it means I have to exclude it by using around brackets. Then I have to say union, then I have to continue the other side. So I have to skip negative 7,5 and then go to the other side of it and then go to infinity. So this is how one can actually write this same thing using the interval notation that we have been discussing so far. You see, but let's look at more examples then. Let's look at more examples so that we can practice this and it get into our fingertips. So another example that you can get is given g of x, which is the function 1 over 3 minus x plus 1 over 3x plus 5. Determine the domain of gx. So this is what you have to do now. So how can we deal with this? So every time when we are given a function and they say find the domain, you must always try to look for things that you know that whenever they are there, we have some information pertaining to them. Like for example, now we have fractions. So what do we know about fractions? So we know that for fractions 3 minus x can never be equal to 0, and we know also that 2x plus 5 can never be equal to 0. So what follows from here? So it follows from here that x cannot be equal to 3, and it follows from this side that x cannot be equal to negative 5 over 2. You see that? So which means we see that the domain of this function is everything except these two numbers. But now how can I exclude these? You see that? So to exclude these now, how do I go? So I'll say domain of g, which I write as dom g, is what? So we see that we take everything from negative infinity, but there is a negative 5 over 2 which we skip. So to skip it, we go to it, put a round bracket and union, then continue from the other side of it to what? So from the other side of it, we'll continue up until we reach a 3, because a 3 also has to be excluded. So we put a 3, then we jump around from the 3, and then we go to infinity, and this becomes the domain that we are looking for. You see that? This is the domain that you are looking for. So we are using union here because this thing is like this. You see that? If I can draw using some number line to understand what is going on here, is like this. We have a number line, and in this number line there are some regions which are not allowed to be part of this number line, and we have a negative 5 over 2 and we have a 3 like this. So which means the domain of this particular function that we're dealing with here, it is these regions. So what we want now is how can we then describe this region using interval notation. So this solution that we have here stands for this region, this one stands for that region, and this one stands for that region. So you can see that this region on the far left, it starts from negative infinity, but it ends before negative 5 over 2. Then we skip to the other side. We start from negative 5 over 2 and we stop at 3. And when we go to the other side of 3, we go from 3 then to infinity, that other side, because these are infinity and negative infinity here and a positive infinity there. So this is exactly how you get to find the domains. You see that? So these are things that you should get used to. Sometimes they cannot give you just a pure hyperbolic functions like the ones that we have been seeing. So what they can give you now is they can give you even a solution in the form of a product. You see that? So they can say, example 3, given f of x, which is the function 3 over 6 minus 2x, and then x plus minus 5, like this, determine the domain of f of x. So that can be another question that can be asked. So how can we deal with this problem that we have here? So again, we look at what we see. So we see that now we have a fraction which is a product of denominators. So we know that if this fraction has to remain valid, none of these factors must equal to 0. You see that? So we know that 6 minus 2x can never equal to 0. And also we know that x minus 5 can never equal to 0. So that's what follows. So it follows that x can never equal to 3, and also x can never equal to 5. You see that? So which means now what we're dealing with is a situation which is like this now. So if we to represent this on a number line, it means this is the situation. Then we have this unwanted point. We have a 3, which is unwanted, and we have a 5, which is unwanted. So the region that we are looking for, it is these zones. So our solution must have 3 parts. So then how is it going to look now in interval notation? So our solution in interval notation then will look as follows. So we'll have x, its dom of f is what? So dom of f is everything from negative infinity, then we stop at 3, then we jump to 3 to the other side, then we end at 5, then we jump to the other side of 5, then we go to infinity. So this gives us the domain that we are looking for. So this is how you get to find the domain of functions like the hyperbolic functions, or functions that have denominators to say. You see that? Now that we have learned how to deal with functions that have denominators in them, let's move on to look at functions that have roots in them. Functions with square roots. You see that? So a function with square root, it is a function of the form f of x is equals to square root of some function g of x, like that. You see? So this is one of the things that you should know. So this thing that is called the square root, there is one nice thing that you should know about it. You see that? So what is it that you should know about a square root? So one thing that you should know about a square root is that square root is only valid if the function g of x, which is underneath the square root, is always greater or equal to 0. You see that? So a rooted function can never work when you put something which is negative underneath it. You see that? So the root function can only provide you with an output when you put things that are positive as arguments. So if you put things that are negative as arguments, you don't get anything out. So only things that can give you solution is you must put things that are positive as arguments. You see that? So which means in general, so this implies every time when you want to find the domain of a function such as f, it is simply x, it is all x element of real numbers such that g of x is always greater than 0 at those points, you see. So that's what the domain is. It is all the x values that make the function underneath the square root to always bring out things that are positive, you see. So how can we then practice this? How can we then practice this? So to practice this, let's look at the following examples. So given f of x, which is equals to root of 3x minus 5, find the domain of f of x. So how can we find the domain of f of x? So the solution proceeds as follows. So first we have to ask ourselves, looking at what is given, what do we know? We know that for the root to be valid, what must be the case? So for the square root to be valid, we know that 3x minus 5 must always greater be equal to 0. So it follows from here that x must be always greater than 5 over 3. You see that? So if we were to represent what exactly we're saying here using a number line, it means we're talking about something like this. So if you have a number line, if I represent maybe 5 over 3, so 5 over 3 maybe can be somewhere here. So how do I represent this on a number line? So on a number line, it means this thing. So I shade here to show that even 5 over 3 is included and we are going all the way that side. So then how then do we write this in interval notation? So we can now say, therefore, domain of f is equal to what? So it is everything from 5 over 3. So I put an open square bracket. So it's 5 over 3 and all the way to infinity. Just as you can see now. You see that? So that's how it works. That's how it works. But then, whenever there's a linear function underneath, it's always easy then to deal with this. So let's see now when we have something a little bit complex. What about now when we are given something like this? So let's say you are given a function h of x, which is defined as a product of two functions x minus 3, then 5x minus 2. So then they will say determine the domain of h of x. So how do you go about finding the domain of h of x like that? So this is a very tricky problem. And people must be very careful how they deal with this problem. So first thing we ask ourselves, what do we know? So we know that for the root to be valid, it must be the case that we know that for this square root to be valid, it must be the case that x minus 3 times 5x minus 2 is greater or equal to 0. You see that? So one of the most common mistakes why I say this problem is very tricky is because most people, they always then come here and say, this means x minus 3 is greater than 0, or 5x minus 2 is greater than 0. So once you do this thing that we have here, so once you do this thing that we have, like this one that we have here, this is completely wrong. You don't do that when you're dealing with a product of functions. So every time when you have a product of functions like this situation that we have here, how you proceed forward is you just find things that are called critical values. You see that? So we proceed as follows. When we're dealing with a situation like the one that we have met there before. So what we do is you find what are called critical values. So for a function which is a product like this, critical values are those values which are such that when you plug them, one of these brackets should vanish. So which means we can see that definitely the critical values here are x is equals to 3 and x is equals to 2/5. So once you have these things that are known as critical values, the next thing that you do is you can represent them on a number line. So we come and draw them on a number line. So on a number line, they will appear like this. So there is 2/5, which sits here, and then there is a 3, which sits here. Then now, after you have drawn this on a number line, our main focus points now, they lie here. So if you draw a number line, you will see that a number line will give you 3 different regions. It will give you this region at the far left end, and it will also give you this region that is in between, and it will also give you this region that is at the far right, like that. You see, so what we're looking for now is a region which contains all values of x such that when we plug them, both these two brackets are positive at the same time. So to achieve that, this is how we go about it. You see, so what we do, we look at the far left, far region on the right, and what we do is we choose any number that lies in that region. Since this region is bounded by 3 on the lower side, it means we can choose any number greater than 3 in this particular region. So when we choose a number greater than 3 in this region, what is it that you recognize? So what you do first, you choose that number. Let's say maybe you choose 5, and what you do is you go and put that number in both your brackets and see what happens. So you put 5 on the left bracket and 5 even on the right bracket. So if you put 5 here, you get a positive 2. Put 5 here, you get a positive number. So a product of positive number is a positive number, which, so we see that this right hand side gives us a positive sign. Then the next thing that you should know is that if you know the sign on the far right, you should always know that from region to region, they always alternate. So which means the sign of this region is going to be a negative, and the sign of this region is going to be a positive. So this is always the case all the time. You see. So now we can go back and see what we're looking for. So we're looking for values where both these two brackets are positive. So the values where these two brackets are both positive, they are the ones that lie in these positive regions, or the regions that have positive signs in them. So we can see now that what we're looking for, therefore, is what? So therefore, the domain of the function, what did you call function? H of x. So let me write it here anyway. So therefore, we can see now that the domain of the function f is simple what? So the left-hand region, it starts from negative infinity and it ends at 2/5. Then we have a continuation of this other region which starts at 3 and goes to infinity. So this is the solution that we are looking for, which is the domain of this function. So it's good to make sure that, yes, you practice problems of this nature so that you can see that you always get the correct domains all the time. You see. Then the next thing that we want to look at is the logarithmic function. So a logarithmic function is a function of the form f of x is equals to log of some function g of x, or at times we can write it as f of x is equals to the natural log, which is written ln of some function g of x. So that's what a logarithmic function is. So examples of logarithmic function, they are function like f of x is equals to log of 2x minus 3, and h of x is equals to ln of x minus 5. So all these things are examples of what we call logarithmic functions. So what is it that you should know about a logarithmic function? So for a logarithmic function, this is what you should know. You see that? So a log function can only give outputs if g of x is greater than 0, which means now we don't have an equal to. It has to be strictly greater than 0. So that's one thing that you should pay attention to, that we have to be strictly greater than 0. So that's what you should pay attention to. So every time when you are given a function that has a logarithmic function in it, and they want you to find the domain can be found by knowing this fact. So if you happen to know this fact, then it's easy to find the domain. So let's see now how we can practice actually how to deal with the problems of this nature. So typical problems that you can get are as follows. So an example will be given the function which is defined as px is equals to log of 9x minus 5. Determine the domain of px. So how can we determine the domain of this px function? So to find the domain, we see a log is involved. So we just invoke the fact that we know about a log. So what do we know about the logarithm? So we know that 9x minus 5 must always be greater than 0. So this implies x must always be greater than 5 over 9. You see that? So since x must always be greater than 5 over 9, it means that's the domain that we're looking for. So therefore, the domain of px, which I'll write as dom p, is just simple. Everything from 5 over 9. So I use a round bracket because this is a strictly greater than, and it goes to infinity. So that becomes our domain thing. You see that? So these are nice problems to practice on all the time when you are solving such problems. Then another example would be as follows. If a function g of x is equal to natural log of 1 over x minus 2, determine the domain of g of x. So this is a very tricky question again, because if you now look here, you have the combination of a fraction and the logarithm. So now you should ask yourself, what do we know? So we know that this x minus 2, which is sitting there, can never equal to 0. So this implies x can never be equal to 2. And what do we know again? And we know also that 1 over x minus 2 must always be greater than 0. You see? So those are things that we know. We know that 1 over x minus 2 is greater than 0. But now, how can we solve this inequality? So I know that most people, they will want to then try and see if maybe they can cross multiply here. So this is a problem also in which you cannot cross multiply. So to solve this kind of problem, what we normally do is, what can I say? You can either sketch the function, that's one way of doing it, but another nice way of doing it is using what is called the table method. So to use the table method, what you simply do is you look for the critical values of this hyperbolic function. So critical values are things that make the numerator to vanish, or the other factors in the numerator to vanish, and also the factors in the denominator to vanish. So which means now we have only one critical value. So the critical value that we have is what? So x is just 2. That's the only critical value that we have. So now since x is just 2 is the only critical value that we have, what you can simply do is you can construct a number line just like what we did before and indicate that critical value. So I create a number line, then put 2. Then what I do now is I look on both sides, because this 2 allows us to construct 2 regions. So I have 2 regions now. This region on the left of 2 and this region on the right of 2. You see, so what we have to do now is we have to study what are the signs that we have in these two regions. So to proceed, now we take any value greater than 2 and we put it into the function. So if you take any value that is greater than 2 and you put it here, what do we get? We only want the sign, we don't care about the number. So let's say I take 10. If I put 10 here, I'll get 1 over 8, which is a positive thing. So definitely it has to be negative. You see that? So now how can we say the domain of X is? You see that? So therefore, what is the domain of F? So we can see now that the domain of G here is what? So we see that it's everything from 2 going this side. But 2 is not allowed from here. So we see from here that 2 is not allowed. So it must be an open bracket 2 to infinity. So everything from 2 to infinity can work as a domain of that function, as long as 2 is not part of it. But anything which is there, because if you look, everything which is there will always give you a positive answer there. So you'll always have an output coming out. So this is how you actually get to work out the domain of all different functions. And all these examples that I've given you, they catered mostly for the functions for which it is complicated to do so, excluding the linear functions, the parabolic, and the exponential. All these other examples, they are the problems that you're going to be getting most of the time when it comes to the domain and range. Problems that have fractions in them, problems that have roots in them, and problems that have the natural logarithm in them, or the logarithm itself. Otherwise, yeah, I would like to cut this lesson here to avoid it being unnecessarily long. Otherwise, thank you for watching, guys. So we'll meet on the next session where we are going to be discussing how to now find the range. So here we just discussed how to find the domain. Now we'll look at almost all these functions and then learn how to actually determine the range of these particular functions. Otherwise, good day.